Bismillahirrahmanirrahim. So I've decided that I will do the Gibbs Sampler today. So that really completes the course, although it's a little bit abrupt. And I won't give examples, but they're all there in the book. So the topic is hierarchical Bayes. So in hierarchical Bayes we have the following situation. I'm going to look at regression models. So we have y equals x beta plus epsilon. Epsilon has a normal distribution, and we can allow for general covariance structures. So this is sigma. There will usually be some scalar associated with this, which is going to be estimated, but the general big matrix will not be. It could be an autocorrelated error matrix, for example, and many other things are possible, but we'll deal with the simple cases. Now, in all Bayesian methods put a prior on beta and one on sigma squared. These are the parameters. The beta and sigma squared are the parameters. And so far we have been dealing with just beta unknown, but actually sigma squared is also unknown. And so what we would have is gamma prior on the sigma squared, or inverse gamma prior on 1 over sigma squared. And a normal prior on beta. So here I am putting a prior on beta, which is that beta comes from another regression model, which is relating it to alpha. And now, yes, E has a normal distribution with mean zero and covariance omega. And so now these are the hyperparameters, alpha and omega. This can be have a t squared. These are the hyperparameters. These are the parameters. And now the empirical Bayes method works by estimating the hyperparameters and then using the Bayesian estimator of beta. So that's the simple thing, and that's what we have been doing all along. Now, the problem is that this is not such a good method in the sense that basically there is uncertainty and lack of knowledge about the hyperparameters, and we are just estimating them, and then we are pretending that the estimate is the true value, just like we are doing for sigma squared. So that's a defect of the empirical Bayes. The correct way to model the lack of knowledge about the hyperparameters is to introduce a model for that as well. So this is called the second stage. So this is the first stage prior. Then we put another prior on these alpha and t squared. So then we have alpha is equal to g gamma plus f, and f is normal and mean zero. And second stage covariance matrix omega 2. So this is hierarchy: first stage data distribution, second stage prior, and a prior on the prior. So this is the hierarchical Bayes model. In this particular case, we assume that G is known, and we assume that omega 2 is known, And generally speaking, okay, we could go fourth stage, but basically we assume that gamma is that there is an uninformative prior, f of gamma equals 1. So it's the same for all. So all values of gamma are equally likely. And similarly, we can assume that omega 2 is equal to infinity, so that there is no that the prior at this stage the prior variances has infinite variance. We have no information, but actually we will not assume that. But the thing is that we will allow this to go to infinity to get the results that we want. So now these are you might call second stage. This is a hyper parameter, and if there is another parameter here, that would also be a hyper parameter. So we have 3 stages, and basically you can think of it like this, that what we do in the original empirical Bayes is that we use classical maximum likelihood type or method of moment type estimators for the hyperparameters. Here we are switching to using Bayesian estimators for the hyperparameters. So it's just one level extension. Originally, you see, the classical method uses maximum likelihood and method of moments for beta. Bayesian adds a prior and assumes that these are known, alpha and t squared are known numbers. So then it uses a Bayesian estimator. Here, now the empirical Bayes says that these are not known, so it estimates these from the marginal distribution, and it uses classical methods. It uses method of moments or maximum likelihood to estimate the hyperparameters. And now the hierarchical goes one step further and says, okay, since these are unknown, we won't use classical methods, we will use Bayesian method. Now to use Bayesian methods, you have to put a prior on these, and now you put a prior, so this is your second stage prior. That's the idea. It becomes complicated to understand, because you have to keep switching between several stages. Okay, so now in order to handle this model, we will do it in 2 steps. At the first step, we will assume that the variances are known, so we won't worry about that uncertainty as usual. The sigma squared is known, t squared is known, omega 2 is known. Now what I want to show is, yes, the first step is this crucial lemma, which is proven in one way in the notes, and I will prove it in a different way here. So y equals x beta plus epsilon, beta equals h alpha plus e, epsilon is normal with mean 0 and variance sigma, e is normal with mean 0 and variance omega. Now I want to get the distribution of beta given y. And so I assert that this is, first the simpler part is to get the distribution of y given alpha. This is the marginal distribution, which doesn't involve the beta, and this is very easy to get because you just substitute. So one way to do it is to say just substitute, so we get y equals x times h alpha plus e plus epsilon. So I just substitute for the value of beta within the first regression. So I get y equals xh alpha plus xe plus epsilon. So now E has mean 0 and epsilon has mean 0. So this is the error term. This is the mean. So y is normal with mean mean xh alpha. And covariance matrix equal to the covariance of these two. Now assuming that these two are independent, then the covariance of these two terms add. The covariance of the first term is x omega x transpose, and the covariance of this thing is just sigma. Okay, so did we do the multinormal linear transformation formulas? It's a very standard result, but it is nonetheless important to know. Let me just recall that if x is normal with mean mu and covariance sigma, and you take any linear transformation, y equals ax plus b, and this is normal with mean a mu plus b, the same linear transformation is applied to the mean, and the covariance gets pre and post multiplied by the multiplier matrix A. This is well-known theorem, easy to prove, and that's what we apply to get the covariance of xe. X times 0 is 0, so the mean is 0, and the covariance matrix is just x omega x transpose. So this is the marginal distribution. Now if we were doing empirical Bayes, we would use this to estimate the alpha. And how would it come out? Well, basically, remember that this is equal to, you would get the Gls estimator for alpha. And in fact, that's what I want to do to prove this. Okay, no, not this part. I'll prove the other part. Okay, the other part is the distribution of beta given y, which is more or less what we have studied before, that is the precision weighted average of the two means, but in this case the means are different and the precisions are a little bit different, the formulas are different. So this is this is a principle that I have been emphasizing, that if you get lost in the formulas, then you will never understand what is happening. So you have to know both the formula and the meaning of the formula. Now the meaning of the formula here is exactly the same, and one that you have studied many times, that the precision, when you look at the data distribution and the prior distribution, then the posterior mean is the posterior precision is the sum of the data precision and the prior precision, and the posterior mean is the precision weighted average of the data mean and the prior mean. And that's exactly what we are going to write down, but the particular form of the expression will be different from what you have seen before. Now there is one proof of the result that we have given in the notes. I'm giving another proof here. So the other proof works by using a methodology which is very important and useful in many situations. That is, in this model, for the data, the optimal estimator of beta is the Gls estimator, which is beta tilde for the Gls is x transpose sigma inverse x transpose sigma inverse y, and the distribution of this beta tilde is normal with mean beta and covariance matrix x transpose sigma inverse x inverse. Now it turns out that this beta tilde is a sufficient statistic, meaning that if you want to do inference about beta, then all you need to do is look at this, everything that you need. So if basically what we are trying to do is to derive the posterior density of beta given y. So the posterior density of beta given y is the same as the posterior density of beta given beta tilde, because beta tilde has all the information about the data. That's one theorem that I just assert without proof. So now I have the density of beta tilde given beta is this one, and beta has this density. So now we apply exactly the precisions idea. So the precision of the prior is omega inverse. So I'm just going to write down the density of beta given beta tilde using the knowledge that we already have. And so I'm going to write that this is some covariance matrix B, where B inverse is the precision of the prior, and this precision is the sum of the two precisions. One is omega inverse, that's the prior precision, and the other term is x transpose sigma inverse x, which is the data precision. It's in the notes. किताब में है, इसको इस पे प्रोजेक्ट कर सकते हैं, ठीक है. All right. So the B inverse is the omega inverse plus x transpose sigma inverse x, which is basically means that the posterior precision is the sum of the prior precision and the data precision, and the other part is that, okay, so this has to be multiplied by the sum of the precisions this is precision plus precision equals precision. So this is the precision. So this is the inverse of the precision matrix, and that has to be multiplied by the precision weighted average of the data mean and the prior mean. I'll just call it B and give the formula for it separately. B is equal to the data mean is beta tilde. Okay, let's look at the prior mean first. So the prior mean is H alpha, and that has to be pre-multiplied by the precision, which is omega inverse. And then we have data mean is beta tilde, and that has to be pre-multiplied by the precision, which is x transpose sigma inverse x. And now there is a little bit of cancellation here. So we have omega inverse H alpha plus x transpose sigma inverse y. This x transpose sigma inverse x cancels with the inverse of this term, which is occurring in beta tilde at the first stage. So these are the formulas, very easy to derive, nothing to it. You can for the posterior distribution of beta in just the one stage model, which we have already studied, except that this is now in the regression context instead of being in the simple without regression. So we were studying this same model in normal data, normal prior, without any regression structure. Now we have the same model with a regression structure. Results are the same. Now the thing is that this lemma allows us to deal with the three-stage or two-stage hierarchical structure, because each of the stages is exactly like this one separately, so we can just do one step at a time and get all of the results. Okay, so the result is theorem 18.1, which is result of Lindley and Smith. Right, so now we go back to the full-fledged hierarchical model. So we have y given beta is normal with mean x beta and covariance sigma. Beta given alpha is normal with mean h alpha and covariance matrix omega. And then alpha is normal with mean g gamma and omega 2. So now, what does the theorem say? What is the posterior density of beta given y? This is what we want. This is the result. Now remember that in the past we have derived exactly the same density, but what we did was we substituted the estimates of alpha and omega into the Bayesian posterior density. Now we want this same posterior density, but now this is going to be a fully Bayesian posterior, in the sense that instead of estimating the hyperparameters, we are going to actually use the Bayesian. Instead of estimating using ML or method of moments, we are going to estimate. We have put a prior on alpha. And now, so we are getting the effect of the prior distribution assumption into the posterior. So this is now, in a sense, the same as what we have done before, but also different in the sense that we are using a different method of estimating the hyperparameter. That's the only difference. The posterior density is the same methodology as before. So now basically what the theorem says is that this is normal with the these means and covariances, where D, the precision matrix, D inverse is the precision matrix, is the sum of two precisions. One of them is data precision, X transpose sigma inverse X, plus the other precision is omega plus H omega to H transpose inverse. So now the what we are adding here, this is the data precision, that's the prior precision. So the prior precision is made up of two parts. One is the uncertainty in beta itself, which is omega. This was the prior precision before. Now the new term that comes in because of the prior of alpha is that alpha also has some uncertainty. Previously this term was not there, H omega to H transpose inverse. This is the term which is measuring the uncertainty about alpha. Previously what we were doing is we are estimating alpha by method of moments or method of maximum likelihood, and then we are pretending that alpha is unknown, is known, so there is no uncertainty, so this term disappears. But now we are taking into account the fact that alpha is not known, and then we are attaching uncertainty to alpha, so that now comes into the formula. So this is the new term which is coming in from the hierarchical Bayes method. So that's the precision of the posterior. Notice that this is an inverse, so when we add this something to the denominator, it will make it smaller. Means that the precision will be reduced, and that's what we want, because we now have more uncertainty than we used to. We were pretending that there is no uncertainty in alpha, and now because there is uncertainty in alpha, so the variance or the precision of the posterior is less we have less information. And that's correct, because actually previously we were making an approximation which was not correct. Okay, so that's one part, and then this is the sum of the precision, and then the little d, which is the mean, is just the precision weighted average of the two things. So, which is x transpose sigma inverse y plus omega plus h omega 2 h transpose inverse h g. That's it. Now, I already got a headache once when I was writing this, so when I was trying to figure it out. So now I have it written down, so I'll let you get the headache this time. So this is actually not difficult, but there are so many little things that you have to keep track of in order to see what's going on. All right, so this is the result, and I'm not going to prove it, although the proof is straightforward and it's actually written. Now, we could do the example, but let me skip that. A little more headache for you. And I will go to the Gibbs Sampler, which finally does what I have been promising all along but never done, which is that we will take care of the uncertainty in the variances. Okay, so the hierarchical Bayes model was available in the 70s and 80s, but wasn't used very much. There was exactly one article that I could find in that period, which, because the calculations required to do the prior correctly were very daunting, very difficult. And so basically the Bayesian theory was more or less unused because the calculations were too difficult. The computing power was not very high, and to do the Bayesian calculations required doing numerical integrations to calculate the posteriors, because the analytical formulas were not available, in fact don't exist. Many of the densities which come up don't have analytical integrals, you don't have formulas, so you have to do them numerically. Now, one-dimensional numerical integration is not that difficult. People have learned how to do that even at that time. But what happens in these Bayesian models is that you have to do multidimensional integration, and multidimensional integration, even numerically, is very, very difficult because it quickly becomes hopelessly unmanageable. So the Bayesian theory was asleep until this thing which is called the Metropolis-Hastings algorithm was invented, and then it was adapted to the Bayesian situation by Gibbs. So it's called the Gibbs Sampler, And instead of calculating the posterior density, what this does, it produces a random sample from the posterior density. Now, once you have a random sample, then using the methods that we taught very early in the course, you can actually estimate the posterior density from the sample. But often that's not needed, although sometimes you want to do that. But if you want to just calculate the mean of the posterior, which is the estimator, then you can calculate the mean by just taking the mean of the sample, and that will be your mean of, that will be an estimate for the mean of the posterior. You can also calculate the covariance matrix by looking at the covariance matrix of the sample. The covariance matrix of the sample will be an estimator for the covariance matrix of the posterior distribution. So once this was discovered, then the Bayesian theory got a new lease on life, and a lot of work has been done in this area, in both the theoretical side, in terms of, and Gibbs Sampler is a fairly heavy computational intensive procedure, so people have worked on the numerical aspects of it as well, making sure that it converges and so on. And on the practical side also, people have been, now it has become routinely possible to do this, and there are a number of softwares written. A large number of software that I was looking for is implemented in R, and there is also a platform called OpenBugs. Bugs is Bayesian Uncertainty by Gibbs Sampler, I think, something like that. Anyway, so what you do is you feed it your model and your data, and it produces the estimates by the Gibbs Sampler. So it's these things are now well known and being used, but not very much in econometrics. So there's a huge amount of room to use these methods. Nobody knows them, nobody understands them in general public. So let me explain the model, and then I will show how we estimate. So the model is the same as one we have been working with. So y equals x beta plus epsilon. Epsilon is normal with mean 0, and now I'm going to keep track of the covariances. So it's S inverse sigma. S is my symbol for sigma squared, actually. Sorry, S is not the sigma squared. S is the precision. S inverse is equal to sigma squared. Right. So that's because I want to keep track of the precisions, because they are the nice things which come in the formulas. So then, of course, we have a second stage prior on beta. Beta equals H alpha in H alpha plus E, and E is normal with mean 0 and variance T inverse omega. Now, in this theorem, I have assumed that the density of S, which is the precision, is proportional to, the prior density is proportional to some power of S. Sorry, no, alpha is already used. So S to the A. Normally this will be like the square root or something. Yeah. This is one specification. Also, we can easily do the same computations with the gamma density prior on S. I am just following the computation in the text because you will have a second chance to look. If I do that, if use a second one, then it might become more confusing. But once you master this, then the extension to the gamma prior is quite straightforward. It should be available in other places by now. At the time I was writing, I couldn't find anything, but I looked for it in a few places and didn't find any easy write-ups, but it should be available. So now, that's okay. Now I need the third stage, right? Yes. Yeah. Okay, so we put an informative prior. So this is data, this is a prior on the parameter. S is a parameter of the model. So this is a prior on the parameter. And now for the hyperparameters, we assume pi of alpha equals 1, which means uninformative prior on alpha, and yeah, a same sort of a prior on T, which is the precision of the prior. So this is the uninformative prior on alpha and on the hyperparameters. So this is again the easiest case. But if we replace this by a gamma prior on S, a normal prior on alpha, and another gamma prior on T, the calculations are more or less the same. The forms of everything remain the same. Now the basic methodology is that what we want is the density of beta and S given everything else. Everything else means that we want to condition on the data and also on the hyper prior. So this is that would be the posterior, and this is basically in the Bayesian context. The posterior is what we use to make inference. Now, as I've said, we cannot calculate this posterior; it's too complicated. Actually, you can calculate it numerically. You can write down the formula for this posterior. We know actually how to do that. So it will be the integral of something, something divided by another integral. Actually, it's two integrals. So you can write the joint and then the divide by the marginal, and Unfortunately, that formula is quite untractable. You can't calculate it. So now what it turns out that you can't get this, but what you can do is you can get beta given S y given T S y alpha, and for all of these 5 things you can get the conditional density given the others. And of course the conditional density of y given everything is known, that's specified in the model. So now what we want now, the basic idea of the Gibbs sampler is that if I generate random sample from this density, and then this density, and then this density, and then this density, and I cycle through this, then this will converge eventually to the, and if I just focus on these two, then this density will converge to the posterior density of beta and S given y. Sorry, beta alpha S and T, not y. Y is the data. So we take the parameters and we take the hyperparameters. Beta and S are the parameters, alpha and T are the hyperparameters. These are the unknowns, and we want to find out what are these things as a function of the data. So instead of finding out what is beta after knowing y, we find out beta after knowing all of the other unknowns as well. And then we just cycle through and we will get the posterior density distribution of all of these conditional on y. And so once we have that, then we just use that sample to estimate whatever we want to about the posterior density. We can estimate the density itself by using the kernel density estimator, or we can estimate the mean and the covariance matrix. If we estimate the mean and the covariance matrix of beta, we will get the estimator of beta, the Bayesian, the hierarchical Bayesian estimator of beta. And we can also find out how much uncertainty there is in S. We can find out the mean of S, that will give us an estimate of the variance, and we can find out how much it varies. We can create a confidence interval. From a sample, confidence intervals are easy to create. You just chop off the bottom 2.5% values and the top 2.5% values, and you have the middle 95%. That's your 95% confidence interval. In the same way you can do for beta, although beta is multidimensional, so you can either treat every parameter separately and you can get 95% confidence interval, or if you want to do them all at once, then you get confidence ellipsoids, because now the things they are not independent of each other, so you have to work with the multidimensional space. So basically that's the methodology for the Gibbs sampler. Now the only thing is that you need to know what these 4 distributions are, and they are given in lemma 18.2 on page 487. Oh, this is the old text. The new one is the PDF file you have may have different page numbers because it's
18.3.
Yeah, 18.3. Okay, so this is normal with some mean and variance with the formulas for the B, which is the precision B inverse, the precision of beta given everything else can be calculated, and the formula is given like the formulas earlier, so I won't write it down. And then B is the precision weighted average of the data mean and the prior mean, and that also has a similar formula. Now the S, that's a slightly different thing. S has a gamma density with a certain number of degrees of freedom and a certain scale parameter which is written. Alpha also has a normal distribution and T also has a gamma distribution. So that's what the lemma does, and the calculations are not that difficult to do, but I won't go into them because what I want to do is to go over the structure of what is happening. So other than the gamma, which we haven't done, but it's quite easy to do in the sense that you write down the density and then you isolate the terms in S and you look at the terms, and they look like S to some power times e to the minus S times something else. So those are the two parameters that you pick up for your gamma density. The same kind of thing happens with the T. So both of these get gamma densities, and then alpha and beta are things that we have done very often before. So you get all of these densities. Now the next thing is, what do you do with these conditional densities? And that's what the Gibbs sampler does. So that's what I want to focus on. You don't even need to calculate these densities. All you need to do is use them in order to get your Gibbs sampler estimator. So the first thing, okay. Now the thing is that when you have, okay, so first what we do is we generate an initial value. It doesn't have, it can be anything. These are our initial values which we will use to start up the Gibbs sampler. They can be anything because the thing converges from starting from any standpoint, and so the way that the Gibbs sampler works is you start running it and you throw away the first 1,000 or 10,000 or 50,000. Actually, there are some tests that you can do which I haven't mentioned. They have been developed since I was writing, which assess how close you are to convergence and whether or not you have converged. So after you have converged or you are close to convergence, then you keep track of what's happening. Otherwise, it's just noise that's being produced in the process of convergence. It's in disequilibrium, so you don't worry about what's happening. So you pick just some random initial values, it doesn't matter. Now, based on these values, you can calculate what B is and what B is and what this B is. And so now what we are going to do is generate a beta 1, which is the first iteration in the Gibbs sampler. So how do we do that? Well, now if I have a normal with mean mu and covariance sigma, then every sigma can be decomposed as LL transpose This is the, there are many ways to do this. This is the lower triangular Cholesky decomposition, which you use in your other ARMA courses. But it doesn't have to be. There are many ways to decompose this. This is called, L matrix like this is called a square root of sigma, and there are many square roots, and you can do it in many different ways. Cholesky is convenient. So now we can write this. So this is so what I'm trying to show is, given x, normal, mu, sigma, how do you generate a random variable x? So that's what I'm trying to generate a beta from this distribution. Now I can calculate the mean. My computer will give me the mean. I can calculate the covariance matrix. My computer. So the first thing I do is I do a Cholesky decomposition of B, and now I look at the. Now the thing is that if I take L inverse x, let me call this y, then this is normal with mean L inverse mu and covariance L inverse L transpose inverse by the linear transformation of normals. So this is normal with L inverse mu and identity matrix. So if I call this L inverse mu y0, then y minus y0 is normal with mean 0 and covariance identity. So let me call this z. Now I can generate a z very easily, because z consists of how many? These are usually k coordinates. So z1 is normal 0, 1, z2 is normal 0, 1. All of these are normals, and they are independent normals. So any method that you know how to generate a single normal, which can be CDF and inverse of rand in Excel, but every language has, most statistical packages have normal random generators built into them, so you don't have to worry about how to generate them. Excel does not have a built-in one, but it almost has. I mean, from random uniform, if you apply the inverse of the standard normal distribution to it, you will get random normal. So again, you can. So I have my z. Now L is known, mu is known, L inverse is known. So y naught is known. So I add in order to get y, I will add y naught to this, and now in order to get x, I will pre-multiply by L. So L times z plus y naught will have a distribution mu and sigma, with mean mu and covariance sigma. So this will be my beta. This is my first random variable, beta. Similarly, alpha, so now actually we have to do this in sequence, although it doesn't matter which sequence. I can go from beta to alpha to S to T. So alpha can be generated in exactly the same way, because it's another normal distribution with known mean and covariance. So beta and alpha are generated. So beta 1, alpha 1. Now I go to S and T. Now S and T have gamma distributions. Now the gamma distributions, again, there are ways to generate gammas. The easy cases arise if the degrees of freedom is half integer. If it's n over 2, then it's very easy, because the gamma with n over 2 is a chi-square density with n degrees of freedom. And so there is a simple Padel method which is based on the fact that a chi-square density is just the sum of squares of normal. So chi squared n is equal to x1, z1 squared. So if you generate n different independent normals, square them and add them, you get chi-squared n over 2, and this chi-squared n over 2 is gamma n over 2, 1 over 2. And then if you multiply this by alpha, then I'm not exactly sure, I think this gets multiplied by alpha. It is either in the numerator or denominator. I don't remember which one. But basically, so that's the only difference. I mean, so basically you create a chi-squared and then you multiply by some suitable constant, and that will give you the gamma density that you want. That will give you your S and your T. So then you have beta 1, alpha 1, S1, T1. Now these things are fixed. You have generated them. Now the second one, you use these values and you get beta 2 conditional on y. Y remains the same throughout. Y is the original data that was observed, and you are conditioning on this in everything. And then but alpha 1, S1, T1. So you generate, you take this distribution, which will now have different values for everything because these alphas are involved in the expressions. And you generate your second random variable. You take this second random variable and feed this. I think it makes no difference. I'm not sure anymore. It's been a long time. But basically what you do is, you generate alpha 2 y beta 2 S1 T1, and then S2 given y alpha 2 beta 2 T1, and then T2 given y alpha 2 beta 2 S2. And now you have your 4 round of second round iterates of the Gibbs sampler, and then you just repeat this, keep on generating random numbers after random numbers after random numbers. And now basically you keep track of the mean and variance of the past 100 trials, for example. And you wait for this to stabilize. So once it starts stabilizing, and it depends on the complexity of the model as to how long this will take. One of my students, Yasmin Bal, did this in Bill Kent for random coefficient models, and I think she used 50,000 as the place where she started. And I have her thesis on my, so you can look at it if you're interested in doing. I think she also had some accelerators and some tests which were developed. So, so basically, okay. So you keep on generating these, and at the end, so let's say that. Let's say that at beta star you have convergence. Actually, initially the procedure that was devised at the time that I was working on it said that, okay, you have to run the process until convergence or near convergence, and then take one observation as your sampled value, and then start the process all over again. So if you run for 5,000 times, then you get one observation, then run another 5,000 times to get your second observation. And there's a reason for that, because if the process is dependent, I mean, if you can't get an IID sample if you keep on going. So if you start anew from fresh, but then that's very inefficient, because it takes 1,000 minimum to get one observation, then another 1,000 cycles to get the second observation. So the alternative method is based on the interesting observation that, okay, let's say beta star is after you converge, and so beta star 1 is 10,001 and beta star 2 is 10,002 and so on. So the point is that these are all samples from the target distribution, the posterior distribution, which is what you want, but they are not independent. So now the thing is that moments converge even in dependent samples. So if you look at beta star 1 plus beta star t, then this is the sample mean, and this will converge to the expected value of beta star, which is the posterior mean. Now the point is that the rate of convergence is no longer going to be 1 over square root of t, which is what happens, that if you have a sample of size 100, then the variance will go to about 1/10 of one sample. This will not happen because of the dependence. So you might need to take a very large sample, but taking another 10,000 observations here is easier than starting up again, and so the dependence. So this is the preferred method. So you just keep running this sampler and keep evaluating the fluctuations in this sample, and then there are many different techniques to assess that you have achieved reasonable convergence. If this was an IID sample, then I know the techniques for assessing. I mean, these are well-known techniques, and generally the standard theory for asking how large a sample you need is based on calculating the variance of the sample and making sure that it's less than what you desire. But here the problem is that the variance of this sample cannot be calculated easily because the dependence is unknown. You can also calculate the dependence, and there are techniques to do that, but these are all complicated things. But anyway, if you don't want to do any computations, it's also easy. You don't need to calculate the dependence. You just keep track of this average and keep monitoring how the mean is changing, and once the mean stops changing by very much, then you stop your process. And that's how I asked Yasmin Bal to do that initially. Now, for the mean, this is enough. Now you also want the covariance matrix to do inference. You want to know what is the so basically covariance matrix is the right thing to do if you have a normal posterior, but very often this posterior will not be normal. So then what you can do is just look at the 95% confidence interval. So 95% confidence interval will be created by taking a sample of size 1000 and dropping the bottom 25 and the top 25 observations, and then beta star low. This would be done coordinate by coordinate separately, and this will be your 95% confidence interval for your first. And so you get your confidence interval, you get your mean, and those are your, or actually you could use the median here. Okay, the right thing to do would be to use the median. So that's your Gibbs Sampler methodology for estimating the hierarchical Bayes model. Okay. Now, there are several examples given in the text of the use of this methodology, and I guess you should study them on your own, because to take one and describe one will take a while. So I think I will stop here. This covers all of the heavy topics, but in order to learn them you will have to do them yourselves. But this provides you with enough guidance that if you want to make the effort, you will be able to follow. It's not difficult.